Good morning, students. In the last class, I stopped half in the explanation of the pure spectra types. This is the last part of this topic. Spectra. What is the spectra is? It's nothing but the arrangement of the wavelengths. In this case, light spectra we are discussing. Spectra means any data arranged in the increasing or decreasing order is called as a spectra. Here we are discussing about the spectra of light, the two visible light I am discussing. In that spectra, there are two types, impure spectra and pure spectra, basic types. What are the example of impure spectra is? Rainbow. In this case of impure spectra, adjacent colors of the spectra overlap. The examples important. Adjacent colors overlap. In the case of the rainbow or just sunlight, if you pass through the prism, what you see is the impure spectra. But we are going to discuss a pure spectra. For experimental purpose, we go for the pure spectra. What is pure spectra is? In the case of the pure spectra, adjacent colors there is not overlap. For example, if you have taken the WIBGR, if you have taken the visible light, violet color, violet wavelengths starting from 4000 angstroms and the red is 7000 angstroms, 7500 angstroms approximately. Nanometers if you take, this is going to be 400 nanometers, this is going to be 750 nanometers. Violet has the colors of the wavelengths. Violet is not a single wavelength, it is a band of wavelengths, and so many wavelengths are present corresponding to violet only. Similarly, indigo is also band of wavelengths only. Similarly, blue, yellow. Sodium light also emits yellow light, yellow color wavelengths. Even potassium also emits a wavelength of yellow only. But each atom has their own wavelengths. But what I am taking here is continuous, all wavelengths are present. That from 4000 to 7000 means 4000, 4001, 4002, like that. All the wavelengths are present. That is called as a continuous spectra. But if you take the general spectra of all wavelengths imagination, and that is compared with any other spectra we are obtaining later of the for the visible cases. Pure spectra is obtained with the help of the instrument called as a spectrometer. This is a spectrometer. It contains a prism fixed in the minimum deviation position to get the bright colors, and without small minimum deviation position, even small disturbance of the prism does not make much difference in the deviation of the light, because at minimum deviation, if you check up this D and I, minimum deviation, this lowest value of the deviation you will find. Even if the small change of the disturbance in the prism position, that I changes by small amount, there is no changes in the deviations. The small changes in the I deviation remains constant from here to here almost. So that prism is kept in the minimum deviation position. And it contains one tube with a slit, small narrow slit and a convex lens fixed at the other end, and the distance between these two can be adjusted to have the focal length f of this lens. So that light rays coming from the focus will become parallel. So what you are getting here is parallel rays. These parallel rays after passing through the prism split into parts. If you take the white light split into 7 colors. If it is not white light, any composite light you have taken, that is split into different wavelength separation. Wavelength separation takes place only for the composite light. If you use a monochromatic light, no wavelength separation takes place. Monochromatic means single wavelength. So here that line which is spreading up, passing through the telescope here. Telescope is why telescope is for the stars only, but stars are planets which are long distances. But light coming from long distance, we consider them as a parallel rays. Here we are taking the parallel rays only coming with the help of the collimator. Collimator function is to produce a parallel narrow beam of light rays, narrow parallel beam of light rays. And that is parallel rays, so telescope we are using. And spectra you are observing means called as a spectroscope. If you are taking the photograph, called as spectrograph. If you are taking the readings with the help of this instrument called as a spectrometer. Same names for the different names for the same instrument. So we are getting the pure spectra for this. Pure spectra example is the spectrometers. Next, in the pure spectra only we are going to discuss now. In this pure spectra again we are going to discuss the two types: emission spectra, absorption spectra. If you read the element materials that emit the spectra is called as emission spectra. In the sunlight, sun is emitting the light, so that is the emission spectra. If you take the candle light, candle, sun, etc., anything that is burning, what is happening during the burning process is the atom gets excited, electrons jump from lower energy level to higher energy level, these charged particles jumping back to the original ground state produce the radiation. That radiation can be in the visible region, then we call it as a light. That light splitting based on the wavelength separation with the help of the prism is called as a spectra. Sun, candle, etc. Next is in this continuous spectra. Emission spectra is of the two types. One is called as a continuous spectra, another is called discontinuous spectra. As the name indicates, continuous spectra, all wavelengths are present in this. Starting from visible spectra if you taken, starting from violet to red. So 4000 to 4001, 4002 and so on, all wavelengths are present. That is called as a continuous spectra. Continuous emission spectra also we can call it as. All wavelengths are present with within the range. Within the range means starting from particular value to ending value. 4000 to 7000. Below 4000 possibility also there means it will be there. Or maybe starting from bluish green, blue or green up to red. Only particular range also possible. That depends on the temperature of the source. That is called as a Wien's displacement law. Lambda m, wavelength corresponding to maximum intensity inversely proportional to temperature. More temperature, less wavelength means high frequency. You will find that based on the temperature, the wavelength range is limited. So, based on the temperature of the material, that spectral wavelength is limited. Like coal, if you have taken, coal is black initially at low temperatures. It absorbs the radiations. If you hit the coal piece to high temperature, it produces the radiations. Depending on the temperature, it may become red hot, light yellow color, like the different colors it may produce depending on the temperatures. If it is producing white light means, it is appearing white means it is producing all possible wavelengths from violet to red. Even if it produces a blue, green, etc., depending on the temperature, which is more intense appearing, even if many wavelengths are present, which is appearing more intense is related to this Wien's displacement light is called Wien's displacement light. It's called displacement light related to the graph. As the temperature increases, lambda m decreases, means frequency and energy increases, it means to say. Next is example for the continuous spectra. Incandescent solids heated to high temperature produce a continuous spectra. Incandescent means what? The metals or solid generally we take as metals which are heated to high temperatures. That means related to those metals. High temperature, high melting point metals. Metals with a high melting point. So when heated to high temperature, they become red hot, white hot and produce the radiations. Red hot means they are low temperature. As the temperature increases, the color changes. Violet means high temperatures. Even if you take the flame of the Bunsen burner, or if you take the gas stoves, we adjust that flame color to violet. If it is colored to violet, it means all the particles of the gas are burnt up and you get the high temperatures. Red flame is produces less heat. Next is discontinuous spectra. Discontinuous spectra do not contain all wavelengths. As the name indicates, do not contain all wavelengths. Some wavelengths are missing here. That example for the discontinuous spectra, two types are there again in this. That one is a molecular spectra, another one is atomic spectra. In the material in the molecular state, this is solid state. Solids, this is solid state. And molecular state, like gases or materials in the molecular state, even if you take the sodium chloride salt, if you have taken the molecular state, if you heat it to low temperature, that produces a discontinuous spectra, which is a molecular state. So, molecular spectra is called the band spectra. Low temperature substance like a candle flame. If you are heating the salt, sodium chloride, magnesium chloride, like that salts, if you are heating in the low temperature flames, what you get is called as a band spectra. It is also called as a molecular spectra. Band of colors, it contains a band of colors, so band spectra. And each band, like VIBGYOR, if you have taken, each band, blue if you have taken, in this blue, the intensity is not constant throughout the band. Intensity is very high at one end and goes on decreasing to the other side. That more intensity position is called as a band head. If you check up with the high resolution telescope, if you observe properly, then what you can notice is the lines you can notice. What are these lines actually is slits. The slit what you are seeing is each wavelength image you are seeing there as a slit images only. So, each wavelength is corresponding to, or each line is corresponding to a particular wavelength, which is nothing but the slit only. If you take the slits narrow, this will be narrow lines we can see, and the white backgrounds. The screen is taken as white background, or directly you can see with the eye. So, here band head is a place where the intensity is very large, but if you see with the microscope, this telescope with high resolution, what you can see is many lines are present, but here line separation is less. As you go to the other side, line separation increases. Less separation is called as a band head. Each line corresponding to the particular wavelength, but how this wavelength produced is, light is produced is by excited atoms here. But in the molecular state, we have the possibility. If you take the molecule, for example, diatomic molecule if we have taken of any gas and heated to high temperatures, then possibility of these atoms can be excited state. Electron jump to the higher energy level and jump back up producing radiations. That is excitation energy, wavelengths are present. Apart from that particular wavelengths you will get. Apart from that, the molecule can have rotational motion. It can rotate along this axis. If it is a diatomic molecule, along the axis possible the atoms energy production is not there. But if it rotates about in any other axis, then it is possible to produce a radiation. That is called as a rotational energies. It has the excitation energy, rotational energy, and possibility at high temperature to have the vibrational energy also. That also produces additional radiations. So, this low temperature substance, band of the colors, band head, excited of the atoms, vibration, rotations. Each one is a different wavelengths they produce. So, all those wavelengths are mixed up. And these excited atoms is the high lambda, but related to the different energies, and vibration and rotational energies have the low energies. So, these low energies are mixed up here, and you go this side, only high energies waves are present, that is related to the excited atom. Here excited atoms, here more of rotational vibration energy wavelengths are also present, they are mixed up here, but more mixing is near to this band head, therefore, you will find less separation, more intensity of the waves. Salts heated at low temperatures produce molecular spectra. Emission spectra we are discussing. Next is atomic spectra. This is also discontinuous spectra. This atomic spectra is important for us. This atomic spectra contains very few lines of the wavelengths, very few lines are present, very few lines of wavelengths are present, and it is called as a characteristic spectra of the atoms. It is called as a characteristic spectra of the atoms. Characteristic means property of the particular element. It is also called a signature of the element. Sodium atom, for example, if the sodium atoms are heated to high temperature, they produce only two wavelengths. One is 5890, another one is 5896 angstrom units. This is called as the sodium doublet D1 and D2s. Atomic spectra, it is also called the line spectra because only few lines are present. Example for this atomic spectra, how do we get is, here is candle flame. If you are heating at a low temperature candle flame, you will get Bunsen flames, you will get the molecular spectra. But if you are heating at high temperatures means arc spectra. Carbon arc, it is called as a arc spectra is another one. Another one is excited discharge tubes. Discharge tubes means ionized gases. Take it as ionized gas. Gas in discharge tube. Arc spectra, discharge tube, ionized gas. I am not writing that place, is not there. Discharge tubes, ionized gases also produce atomic spectra. If you take the discharge tube like a tube light, and particular gas you take inside at low pressures and apply high voltage between these two, plus minus, electrons jump from minus to plus and they go and hit with the atoms and exit the atoms, then they produce a radiation. Depending on the type of the gas you are taking, what you are taking, that gas is important here, that wavelengths only particularly you will get. Particular wavelengths only you are getting of nature of, which depends on nature of that material. But apart from these gases, because the glass is also present surrounded by these gases, the glass also produces radiation. Some mix-up wavelengths will be present because of the impurity of any gases present, or the electrodes also produce radiations depending on the metal of the electrodes, and also if electrode is heated up, then that produces a continuous spectra. But we are talking here is excitation of these atoms only, and the glass also can produce some wavelengths that will be impurity in the spectra. So, discharge tubes and arc. Arc means two carbon arc rods are taken, separated by some distance. Even aluminum also used sometimes for this production of the arc, but carbon arc is more famous, more intense light you will get. Two rods are taken of the carbon and connected with a high voltage at high currents, high voltage and high currents, and they touched and slowly separated. Then high very bright light jumps from one carbon rod to other carbon rod. Actually, it is an electron jumping. We can't say the electron, it is like a spark, but you will see only light, very powerful light jumping from one rod to other rod, minus to plus. Actually, we don't notice that, but because the gas gets heated up, it bends, the arc bends, and later one will be going upwards gases that pushes the arc up. The result is the bright arc, that bright spark looks like an arc. So, it is called as a carbon arc, because carbon rods are used here, called as a carbon arc, or simply arc spectra I can take. At this point, the temperature is very, very high. If it is a sodium chloride salts put in this arc, the sodium chloride splits. Sodium chloride splits into sodium atoms and chlorine atoms. So, now what sodium chloride together is a molecular spectra you will get. But sodium and chlorine separately you have to mix it up in that also, but you will get the separate valence corresponding to sodium and also chlorine. That you can check up the spectra obtained from the sodium chlorine burning up. sodium atom line separately, chlorine atom line separately. So, that is related to the line spectra. If only sodium is present, you will get only these two wavelengths in the salts heated up, or metal which is heated to high temperatures in the carbon arc or in the discharge tubes. Next is absorption spectra. In the case of absorption spectra, light from high temperature sources passes to the low temperature absorbing medium, which is supposed to be transparent medium. So, if you take the glass tube you take, and there is a low gas you take at low temperatures, absorbing medium at low temperatures compulsory. This is low temperature, and light coming from high temperature source. Light coming from high temperature source passing through the material which is transparent absorbing material at low temperatures. Then what happens is these material absorb some wavelengths to get the excited state. So, some wavelengths are absorbed here, many wavelengths are coming here, some wavelengths are missing here, and missing wavelengths pass through this prism to get the spectra. That spectra is called as absorption spectra. Once again, when the composite light is passed through low temperature absorbing medium, then the spectra obtained is called as the absorption spectra. This absorption spectra, again different types are there. This material which is absorbing can be solid state like a glass, or transparent color sheet. If you put in front of your eyes, that absorbs some radiations and permits only other colors to pass through it. Then it is possible to have continuous spectra is also possible if you take the solid transparent colored medium at low temperatures you are taking, then it can absorb the particular band of wavelengths. So, it is called as a continuous absorption spectra. It is also possible if you take this material in the molecular state, we will get the molecular absorption spectra. Continuous absorption spectra, molecular absorption spectra, and also line absorption spectra is also possible. This is important for us. Line spectra is important here. So, if you take this gas, for example, sodium vapors you have taken, that is at high sodium atoms. Here also composite that you are taking. Here sodium atoms you are taking at low temperatures. Then the sodium atom absorb what it can produce, what valence it can produce, same valence it can absorb at low temperatures. That is also called as the Kirchhoff's law of thermal radiations. So, these sodium atoms can produce the two valence only 5890, 5896 angstroms. So, these sodium valence can absorb same valence. So, if you take the white light passing through these sodium vapors, here in the spectrum two valence will be missing. Those missing valence what you see is the dark lines. If the background all colors are present, whatever valence is missing, that line appears as the dark lines. So, in this case of the absorption spectra, what you find is missing valence seen as a dark lines. Example for this absorption line spectra is a sun spectra. Sun spectra appears to be continuous, all valence appear to be present, but not actually present. Example of the line spectra is sun spectra. Okay. In the sun spectra, it looks like all valence are present in the sunlight when you observe passing through this prism, but all valence are not actually present. If you compare with the continuous spectra, some valence are missing. The missing valence appears as a dark lines. The missing valence appear as a dark lines in the white backgrounds on the screen of the screen. Those dark lines of the sun spectra are called as the Fraunhofer lines. These are important ones. The sun temperature, insert inner temperature in the order of 10 to the power of 4 kelvins, more than 10,000 degrees centigrade will be there, then 10 to the power 4 to 10 to the power 5, something like that. And the temperature, this inner temperature, the inner surface of the sphere is called as a photosphere. Photo means light only. So, there it is called inner core surface called the photosphere. It produces all possible valence, means it is supposed to be white, but light coming out as you go from outwards, the temperature goes on decreasing. The outer surface temperature is low temperatures. Inner surface is 10 to the power 4 Kelvin, something like that, or 10 to the power 4 to 10 to the power 5 degrees centigrade. But outer sphere temperature is only 5,000 degrees centigrade plus 273 means approximately same I am taking something approximately I am giving around 5,000 degrees centigrade. So, this temperature is low temperatures. It is the inner surface high temperatures. So, all valence are produced from here, but passing through this outer sphere called as a chromo. Chromo means color. What you see the disk is a colored disk. This chromosphere absorbs some wavelengths which are depending on the atoms present in the chromosphere. These atoms which are absorbing the valence will be missing on the earth. So, if you observe this spectra on the earth whatever the valence absorbed by this chromosphere we cannot see it. But these atoms in the chromosphere also can produce the wavelengths of their own, and because of high temperature the material is not in the molecular state, it is in the atomic state. is related to atoms, this is related to the molecules. So, these materials in the whatever elements are present, there will be the atomic state. Actually, plasma is present inside one. You can find these atoms at a 5000 degrees state nearly plasma, or you can find them as a atomic state, but not in the molecular state. Plasma state means what? Inside the temperature, the nucleus will be present, which contains the plus minus, and the electrons are not revolving around the nucleus, they are separately moving. That is called as the pure plasma. Any ionic state, just losing one electron, gaining extra electron, ionic state is also called as a plasma, but that is not a pure plasma. On the sun and stars at high temperature, you will find a plasma state, that is the fourth state of the matter. It is also called as ionic state, but just ionic means losing one or two electrons. No, complete electrons are tied off. Nuclei and electrons will move separately. This is called the naked nucleus without electrons. That is called the pure plasma. So, at this temperature, at high temperature, you are very high temperature you are taking, and some wavelengths are absorbed by the chromosphere at low temperatures, and that those wavelengths are missing on the in the spectra observed on the earth. Those missing wavelengths are called as a Fraunhofer lines. They are the dark lines in sun spectra. They are nothing but dark lines in sun spectra. What is the advantage of these dark lines is, these lines help us to identify when any missing wavelength is present, means we can identify that a particular element is present on the sun surface. That is how helium was first discovered. Helium was first discovered on the sun surface with the help of these Fraunhofer lines, before it was discovered on the earth. So, next, how do we know that elements are present actually? Missing wavelengths means the photosphere might not be emitting, but how do you know is related to the total solar eclipse. During total solar eclipse, the moon comes between the earth and sun. This is the sun, and here is the earth. In between you will get the moon. Moon is in the particular space in between these two, thus that light coming from the sun is obstructed by the moon on the earth, so that you cannot see the sun for the particular duration. This sun appears completely covered by the moon, therefore, we cannot see the sun. It looks like a dark place. So, total solar eclipse I am telling, not partial eclipse. And in this case, total solar eclipse time, the moon is coming here and blocks the central portion. When it blocks the central portion, that portion we cannot see the photosphere portion. We can see only outer sphere, that is called as the chromosphere only we can see it. This chromosphere emitting radiation, so we can see, that means complete darkness will be there here. Around this you will find a small light, bright light. These are at low temperature. Now, we are stopping the actual center light coming from center, all radiations, but now we can see only the radiation coming from the outer sphere. That is also present previously, but of very few intensity present. Now, the center one is stopped, therefore, the only dark lines which are missing previously, for example, sodium is here. The sodium lines only can be seen here, or helium is there. Helium lines only can be seen. Helium, every element of the periodic table has its own characteristic spectra that is related to the line spectra or atomic spectra. So, this particular valence, if it is now produced, but when it is completely observed, when the total solar eclipse is not there, that time what spectra observing is, these lines are present. But in the spectra, the other lines brightness is very high, therefore, these wavelengths which are very few intense lines appears as the dark lines for us. So, helium was first discovered on the sun with the help of these missing wavelengths or dark lines, which is nothing but Fraunhofer lines, that is called as a line absorption spectra, outer surface of the sun absorbing the radiations, some wavelengths coming from the inner surface. And this spectra which you are observing during the total solar eclipse is called as a flash spectra. Why it is called flash means what? Because only for short duration that light moon covers the sun, not continuously. So, after that what happens is the surface appears to be bigger of the sun, and you will see the diamond ring, the brightness increases of the sun. As the moon passes away, the brightness of the sun increases, and that's why only for short duration you are seeing the spectra is called as a flash spectra. Okay. With this topic is completed.